So these are just refreshing on some terms because I'm gonna say those words. Like I'm gonna say circumference, I'll say radius, I'll say arc length, and I might say, or I might use the circumference formula. So just keep these in mind when they come up, or you could just go back to this slide, slide number 5. Full circle, like so, we do end up at 360 degrees, right? So full circle is indeed 360 degrees. Um, and again, oh, somebody's noticing those red fractions that have a pi in them. Yes, I know my circles look really crooked, but yes, awesome. We're going to talk about these things. These are great notice and wonders. Someone else said something that I really wanted to point out. We are wondering what they represent. And is there another way to solve it? I like this one I wanted to highlight. I wish I could highlight. This isn't Padlet, but I wonder if all the 3 different colors equal to each other. So like, are they all equivalent? Like when they're written like that. I love that. So there's noticing about those fractions that are in red, the pi. Ooh, here's the last thing I'm going to point out. Again, I wish I could point out all of this, but I'm trying my best to point out like the parts that are going to lead us into the next thing. So Blaze here said, I noticed that 2 pi is equal to 360. So let's investigate that. I'm going to go up. So notice that 2 pi is equal to 360. Is that correct? So according to Blaze, they're seeing these as 2 equivalent things. That 360 degrees is equal to this thing in red, 2 pi, right? So that's that was a notice. Now I'm going to say this to those wonderings. Yes, these are equivalent. So first off, these are equivalent measurements. So 90 degrees is going to be equal to something called pi over 2 radians. 120 degrees, it's equal to 2 pi over 3 radians. So that's what we're going to learn today. That stuff that's written in red. It's called a radian measure. Wow. So it's awesome that your thoughts were already leading us there. So awesome job, y'all. Let's go ahead and go to the next slide to kind of learn a little bit. Let me go back up to my pacing. We are on slide 3. All right, everyone. So let's talk about this. Sometimes when we talk about rotations, right, we like to describe things in degrees, like 0 degrees, 90 degrees, 180, or for example, if you're doing a 360 in skateboarding or walking, or sometimes people use, do they use, now y'all can correct me if I'm wrong, what is it when someone changes their mind and someone says they did a complete, was it 180 or 360 that they say? Let's see what's in the chat. I don't know. I know I hear people say it. It's a 180. So for them, it's kind of like, for me, I would say they did a whole 360, but 180, I think makes sense because 180 is like flat. So it's kind of like they were on this side, but now they're on this side. So it makes sense. So they did a complete 180. It's like they're using degrees. Yeah, to kind of describe even like a situation. So it's like we're so used to talking about degree measurement, even in our casual conversations. Like, love it. So easy. So the radian measure relates more actually to the radius length of a circle. That's where its name kind of comes from. So radian kind of sounds like radius. It relates to the radius length of a circle. So for example, radians are going to help us in this case. Let's think of something like 45 degrees. I tried my best to make this angle look like 45 degrees. But let's just imagine there's an angle that's 45 degrees. And let's say that I want to describe the distance that like some rolling wheel is covering. And let me just draw in this rolling circle. Let's just pretend this rolling circle rolled about That looks more than 45 degrees. Well, let's see. Let's just pretend 45 is like right here. Let's just say that this is about rolling of 45 degrees or something. Say 45. And then in that 45-degree roll, it probably covered like this much of a distance. And I want to say, it wouldn't make sense to say that the ball rolled 45 degrees. It wouldn't make sense because how can we measure 45 degrees on the ground? That's one thing to think about. So this is why we need the angle measure to be represented in radians, because that's going to relate to the radius length of the circle. It's going to actually be able to provide us a distance that we can measure. So if my radius length is like in inches, if I know that the radius is in inches, the radian is going to give me a measure that will help me in inches. So we're able to kind of record the distance a rolling wheel covers if we kind of switch to radian. So that's kind of like the why. Again, the radian measure relates more to the radius length of a circle. Let me know if anyone has questions on that, but that's the why are we trying to use radians now. But we're still using degrees. We're just adding in radians. And a degree measure is going to have an equivalent radian measure. Okay, that's all in good. Now let's go ahead and define, well, what is a radian exactly? How do we figure that out? Let's all go ahead and transition to slide number 5. And don't worry, we're almost going to have time where you'll put your thoughts down so that I could get a feel of where everyone's at. Okay, now for the moment, I want you to kind of ignore these two boxes or these two photos. And let's focus on this one here. It's like on Desmos, it's kind of like not a slide. So it's hard for me to pop up things, but let's focus on this one. So I'm going to describe to you what a radian is with these visuals. Okay, step 1. Let's say you have a circle. You go ahead and you draw your center of your circle, and we just call that O. You could think of that like origin or something. And then you go ahead and you draw a radius inside your circle. We call that radius R. So that's step 1. Let's think of that as step 1 into determining what is a radian. So 1. Okay, sounds good. If we got that, awesome. We just drew a circle, we drew a radius, we called that R. Whatever R is, R could be anything. It could be any length. Okay, now step 2. This is what we do next, everyone. Imagine that you take this radius length R, right? Let's say you take it, you color it in red. Let's say you take this length and you're going to drape it along right here. You're going to start to drape it where this line intersects the circumference. And I'm just going to drape it or just drop it down there. And it's going to curve. Kind of think of it like this length is like a string, and I'm curving it on the circumference. Because I just basically took this length and I draped it up here, right? This red line right here. That's just going to have the same length measure as R. So that's step 2. And I'm just trying to see if there's questions. Unmute or use the chat, either one. So that's step 2. I took my radius and I draped it along there on the circumference in red. And I'm just noting that this is the same measure. It's called R, and it's the same measure as my radius. Okay. Now let's see what happened in step 3. Step 3 is all I had to do was where my radius length kind of ended, I went ahead and I drew a segment down back to the center. And when I draw this segment, right, let me change my color. When I draw my segment back down to the center of the circle right here, it's going to be measured as length R, because remember everyone, no matter where you draw a line from the center to your circumference, they're all going to be the same length R because it's a circle. So that means if I was to draw this line down here, this has to measure also R. So that's what I did next. And what I virtually did to kind of go back to our definitions is I created an arc length. Remember that definition on our slide? And if you don't, let me just show you. Definitions, boom. What I did is I created an arc length, but I created it using the radius of the circle and draping it along the circumference. And I created an arc length is what I just did right now. So I'm going back, using that vocabulary. So that is what I just did right here. I created an arc length. Now, what is the measure of this angle? Let me tell you all. The measure of this angle is going to be 1 radian. That is the definition. 1 radian. That is how we come up with a radian right there. We'll go ahead and take a moment to process what we just did. So this measure right here, it is 1 radian. And take a look at what we just did. We took the radius measure, we draped it along the circumference. We drew back another radius length down to the center. And whatever that angle is, right, that angle that we made when we created that arc length, that is called 1 radian. So that is how we define 1 radian. And we're going to see how that's related to degrees, or how we can even convert from degrees to radians in a bit. But I just want to make sure that we're okay with this process, and we'll have some time for questions as well, but feel free to ask them in the chat. Okay. And again, feel free to be taking notes on the slide for anything that was mentioned. Okay, now question 6, everyone, is going to involve some participation right here. So let's go on to slide 6. Dang, Pierre. How did Pierre already get an answer? Okay, so now that you're on this slide, right, we're going to go ahead and now investigate. So how many radius lengths do you think, like how many of these segments do you think it'll take to kind of cover this full circle circumference? All right, everyone, please make sure to go ahead and put your best guess. So here are the different answers we're getting. Just to tell you, when I tried this using my hands, I'm really bad with measurements and my hands move when I do that. So I don't know why I keep doing that. But anyways, I got 5. That's what I got when I used my hands. So I see 5 or 6. I'm seeing 6 come up a lot. 6.5. We got some reasoning. Ooh, look at this mathematical reasoning. So this one says it looks to be around 8 because it looks like it's a 45-degree angle. Oh, whoa. So they're saying like 45 degrees and they're using that. Oh my goodness. It's amazing reasoning right there. 5 or 6. We got about 6 and 5-ish. All right. That seems pretty much like everyone's in agreement. The 8 was the only one that was a little different, but I love that reasoning. Like 45 degrees, and how many 45 degrees in a circle. But all right, y'all, ready for the answer? How much was it? Wait, let's see what's in the chat. Awesome. You could read that. I'm going to just go ahead and re-explain it right at the bottom. So we know that a circumference of a circle formula, as I showed you in the beginning, is 2 pi r. But remember, our r is basically our radian. So let me just go ahead and type radian. Okay, cool. So then that means, what that therefore means is that it's going to take 2 pi radians to fill the circumference of a circle. And some of you remember what pi means, but if you don't, pi is about, and let me just underline that, pi is about 3.14. So if 2 pi radians is my circumference of my circle, Let's go ahead and try to figure out what 2 pi is. All we got to do is do 2 times 3.14 because that's what pi is, 3.14. It's actually more than 3.14. You know, it's 3.14 and blah, 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 blah. There's like more, it keeps going. Let's just round it to 3.14, multiply by 2. I'm using my phone. I got 6.28. So about 6.28 radiuses cover the circumference of this circle. So 6.28. And I also put the formal way to say radiuses. It's radii. It just sounds weird to say radii, but that is the formal way. 6.28 radii cover the circumference of the circle. Radii is the plural for radiuses. That's the proper way. You shouldn't say radiuses. Don't say that in college. One. Someone said that, remember at the beginning, when we were looking at notice and wonder, somebody said that 360 was equal to 2 pi. So someone said that is equal to 2 pi. I can't type out the actual pi symbol, so I'm just using pi. So that was something someone said. That's exactly precisely what we're going to use to convert between radians and degrees, everyone. 360 degrees, if you go around a full circle, that is 360 degrees. Also, if you go around a whole circle, that is 2 pi radians that covers the full circle. Therefore, these two measures are equivalent. That is correct. Well, what do we do with that then? So what we have is, let me rewrite it down here. Let's rewrite this in math language. If these are equivalent, that means 2 pi radians is going to equal 360 degrees. That's what it means in math language. Okay, so we have this equivalency. Awesome. I'm going to now try to simplify this equivalent expression to something nicer. Let us divide by 2, both sides. If you do it on one side, you got to do it in the other. 2 divided by 2 is simply 1, or you could think of that as canceling out. And then we're going to do 360 degrees divided by 2. Let me know if anyone has the answer to that. What's 360 divided by 2? Maybe in the chat, or you can unmute. We've got 180. Perfect. Thank you. So to the 3 of you for saying 180. I see you. Thank you for your engagement. That is right. That is equal to 180. And then we have degrees. So pi radians is equal to 180 degrees. We're going to be using this to convert between degrees and radians. How that's going to look like is we're going to use either, and I'm going to write it, let me write it over here. We're going to use either this expression, pi over 180 degrees, or we're going to use 180 over pi. And why do these work? First off, I want to remind you all, these 180 degrees is equivalent to pi. That's what this equality symbol means. That means this represents a unit of 1, because 180 divided by pi, if they're equivalent, that means they represent 1. Like anything divided by itself is 1. So we're going to use these to convert. So these are the formulas for those important that I just talked about. Go ahead and put your contribution there into the slide number 9. And this is just a little checkpoint to see like what we're grasping here at this point. Use the cross cancel to get pi. Oh, like what we did, dividing by 2 both sides. I agree. That's awesome. And how a circle can be broken up into sections and we can make those equivalent expressions. Wow. Yay, Francisco showing that pi. Wait, can I do it? No. I don't know how you guys can do that. How do you do that? Oh, well. Option P. Option P. Wow, thank you. But mine looks like a square. Thank you. Wow, that's cool. I got it. Thanks, Francisco. Wow. I'm always learning something new from everyone. Not just in like politics. Francisco also got some skills with the keyboard. Awesome. All right. Cool. So now everyone, what we're going to do is take a look. Well, how do we use those two things that I just said, the formula, to actually convert from radians to degrees and vice versa? What I have for you is a video recording. So the reason I'm doing this is because I can't put my slides in here. So I just decided to record myself doing it, the examples. And we're going to look at these examples. And as you're looking at the examples that I'm doing, you're going to have the option, see in your view, you have the option to go ahead and put any clarifying questions in the chat. And it looks like we're going to stop here on slide 10. Questions were coming up. Oh, okay. Or if you didn't put it in yet, go ahead and put any questions that came up for you on slide number 10. And what we'll do is we'll use this as our checkout today. So this is going to be our checkout today. And then we could come back to any questions that are coming up. And what's going to happen in our next class period is we're going to go ahead and try to get some practice in doing our own conversions between radians and degrees. But yeah, go ahead and fill out any questions. If none, that's awesome. But if you do have some, please let us know. Don't worry, you'll be anonymous. Okay, so I see two different questions. So right now, what were our big findings, the big ideas from last time? Remember, we're trying to kind of really deeply understand what is a radian, how does it come, where does it come from, how do you create one? And the best way I like to think of it is using this image. A radian is when you create an arc length that has length r, which is your radius of your circle. So that's basically what we did. But just to better synthesize it in formal language, it's down here. So it's on your slide. So a radian is a unit of measure for angles. So it's another way to measure angles. And it's based on the radius of the circle. If we imagine, the same thing, we take that length of the radius, wrap it around the circle, and the angle that's formed at the center of the circle by this arc, we define that as 1 radian. So that was a huge thing that we constructed. So this angle measure is called 1 radian. That was like how we created that definition there. So whenever you have R like that and an arc length, that is defined, that angle measure is called 1 radian. Again, let me know if anyone has questions about this, but this is again synthesizing the big ideas that were coming up in that Desmos lesson that we did together. On the Desmos activity, we imagined how many radiuses cover the circumference of the circle. The answer was about 6.28. 6.28 is equivalent about to 2 pi. So that's where that came from. So 360 degrees is equivalent to 2 pi radians. We took this equivalency and we created an equation. 2 pi radians equals 360. Now, some of you in the checkout were saying, well, why is it 360? I mean, why is it 180? Why are we doing pi over 180 instead of divided by 260? Because first off, this formula is nicer, right? It's shorter. And for this one, why? It's because what we did is we divided both sides by 2 to get this nice and simpler formula. So this divided by 2, you just get pi radians. And then 360 divided by 2, you get 180. So this is a shorter, nicer formula to use when we convert. And that's why we're either using pi over 180 or we're going to use 180 over pi to kind of convert between our units. So that is kind of addressing a question that came up. and also kind of refreshing everyone on what we did. And yes, thank you, Janet. So because it's 1, I love it. Yes, love that. And then I also found this here image helpful that I'm also going to add because I'm still creating our big ideas packet. I'm going to make sure I add this on our big ideas packet. And actually, this is a nice diagram because it kind of shows you which one of these to use. So if I want to go from radians to degrees, let's say I want to convert from radian to degree, the one that you're going to multiply by is the 180 divided by pi. If you want to go from degree to radian, see the arrow? If you want to go from degree to radian, you're going to multiply by pi over 180. So that's like a little nice chart for you if you need some extra support to decide on what to multiply by. But ultimately, what it ends up being is that you're going to multiply by whatever you need to cancel out. That's how it kind of works out. But here's a diagram if you need some support on that. So I really like it. Okay, now let's synthesize all these visuals into some big idea chunks. So again, the big ideas, 2 pi radians was equal to 360. And from that, we got this simplified equality formula. And down here, you convert radians to degrees by multiplying by 180 over pi. And you convert degrees to radians by multiplying your expression by pi over 180. So these right here are the skill. So we just went from a concept, like what is a radian? We created like kind of like an equality or a formula to use to kind of convert between the units, because you can use either radians or degrees to talk about an angle. So we're going to talk today about how to actually do those conversions. Taking away that multiple of 10, top and bottom, and then I just got 6 pi right here. And then we're left over with 18 radians. And then what I had to do is 6 pi over 18, I reduced it to pi over 3 radians. So that's how I converted 60 degrees into radians. Let me pause. So let's see, because I know there's like a majority said there was no questions, but is there any questions on this example? I know I just verbally went through it right now. 5, and were you asked to convert that to a degree?
Degrees, I think. Yeah.
Okay, so 3 pi over 5. Let's do it. Okay, so 3 pi over 5. So let's try to convert that to degrees. Now here are the 2 different things we can use. Now because I kind of want to get rid of the radians, and this is a radian. Whenever you see the pi symbol, that's going to be radians. I'll just call it rad. Whenever you want to get rid of the radians, you're going to use the multiplier that has the radians in the denominator position. So I'm going to use that one. And yeah, oh my gosh, I know y'all, Khan Academy is going to be it's going to be picky on how you're simplifying. So, but I do encourage you to click the get the hint button, and they kind of
I
show
did.
you.
I did, and it was like it didn't really give me like a
Like,
full like explanation.
okay, okay, I got you, I got you. All right, let's go ahead and talk about it then. So I thank you so much for bringing this problem up. That way we kind of get some more exposure, because actually one thing someone else said was we need more examples. So I love it. Okay, let's see. Let's look at this. So what cancels out so far?
The radius,
Yes, perfect. What else can cancel out?
degrees,
So here's a degree symbol, right? But then I don't see no other degree symbol. So what's something else that's kind of the same, but there's
Pi.
who said what was that?
Pi.
Pi? Okay, so Francisco, you're saying pi. And
Yeah.
by the way, the female that was talking, I don't recognize voices well, but who was talking right now? The original talker.
Jenny.
Yeah. Okay, it usually shows me the name, but it's okay. Thank you, Janet. Okay, so do you see, Janet, why it would be pi? Because we have a pi up here and we have a pi down here.
Yeah.
So
I
when it,
thought I thought we weren't gonna be able to like cancel it out because it was a 3 and the other one doesn't have a 3. So I was
that's a good thing to point out. So actually, yes, you can still cancel it out for sure. Yeah, because I could see what you mean. Because let's see, like in example 2, right? You don't see that there's a number in front of this pi when I canceled out. Is that right?
yeah.
That makes complete sense. So I love that you brought this example up, but we could still do it. So boom and boom. So now what we have is basically all we're left over with is 3 times 180 degrees. And y'all let me know what that is. What's 3 times 180? You use a phone or something. It's hard to tell quickly. 3 times 180.
540.
540. And then there's probably some in the chat. Y'all probably said 540. And then because we did not cancel out degrees, you're still left over with degree symbol. And then we still have something in the denominator position. That means we're still dividing.
Let's divide
And
by 5.
perfect.
108.
108.
Yeah.
There we go. So that would be how, for that particular Khan Academy example, how you would simplify that into degrees. Lovely. Thank you so much for asking this. And let's see what's in the chat. Okay, perfect. So we got the pi and we got the answer of 540 when we multiply 3 times 180. Our learning target, as we transition out of, talking about radians, is I can explain the components of the unit circle. As you know, in this Desmos, I did show you the fully complete unit circle. We actually now finally understand these red ones here. These red angle measures are radian measures. Y'all, if you were to actually sit down and convert each of these degree measures, let me see, like for example, like let's say you took the time, okay, I'm gonna convert 360 degrees to radians. You're gonna get 2 pi as your radians. I'm gonna convert 330 degrees into radians. You're gonna get 11 pi over 6. So we now kind of get where these red parts are coming from, these red radian fractions. That is what we just learned. So like I said, you could verify this yourself and do the calculations, but that's what they are. So that's great. We kind of already got one component of the unit circle taken care of. Now let's talk about how this works. How do we use it? How do we measure on it? First things first, this is how we usually are going to measure angles on the unit circle. So you kind of have to imagine that you have like a ray that's on the positive x-axis here. So this is the positive x-axis. We call this the initial side. And it kind of opens up to create an angle. See, it's opening up to create an angle. This side right here is called, or this ray right here is called your terminal side. And it measures angles around the unit circle. Now, the terminal side moves around its vertex to create these angles. So let me show you. Let me use like a straight thing. So let's say if I want to create a 30-degree angles, I'm going to draw my initial side right here that's flat. And then I'm going to imagine that I lift up the terminal side to make a 30-degree angle. I'm going to lift it up to here. That is where the 30-degree point is at. Boom. So that is my terminal side. This is my initial side, and that's the 30-degree angle, which is equivalent to pi over 6 radians. That's how I would kind of create the angles on a unit circle. What is this? It's like a cheat sheet. Yeah, it's kind of like a cheat sheet. Yeah, to be honest, except, oh my goodness, when I was in high school, we had to memorize the unit circle. I'm not going to have y'all do that. I mean, I probably would have done that for maybe extra credit, but there was like different techniques to memorize it. Like you had to memorize all the radians and all the coordinates too. But I remember it didn't make sense to me. Like, I don't understand like where all of this is coming from. I didn't learn what a radian was. I just knew I had to memorize it and it was part of the unit circle. But now at least you all know what a radian is though. So that's good. And then Ms. Lister forgot what the y-axis is. Hey, that's okay. That happens. Summertime, I forget all my math, so no problem. Okay, so that is kind of how you draw an angle on the unit circle. Again, I like to use this. That's exactly what you're doing, but you're doing it within the unit circle. So initial side is on the positive x-axis. The terminal side is the ray. So you call this like a line that has a little arrow on it. You call that a ray. It's just a definition, is the ray that rotates about its vertex right here to measure the angles on the unit circle. So you just could open it and rotate it around to measure angles. And someone mentioned this on the Desmos, which was cool. They were saying that the angles on the unit circle were were kind of growing counterclockwise. That's exactly correct. That is part of the definition of what is a unit circle. How we create angles, positive ones, is we move the terminal side counterclockwise. So that means, you know how the clock usually moves this way? Like if you're looking at a clock, even though clocks are now getting outdated for phone clocks, but usually clocks move this way, the hands move this way, but counterclockwise means you're moving kind of opposite of how a clock moves. So you move counterclockwise to measure positive angles. And well, then what happens if you were to move clockwise? What if you were to move in the opposite direction, like a clock? You actually move the terminal side clockwise to create negative angles, everyone. So you can create negative angles on the unit circle. So that was, if I was to do this and move backwards clockwise, this would be a negative angle. And we could just say, I don't know, negative 35 degrees or something. And then you could convert that to radians, to whatever that is. You would do it the same way, except just make your radian negative. So that's just how you would create negative angles. You move down backwards. Let's see if anyone has any clarifying questions about any of this so far. Here's are just the bullet points of things I was explaining verbally and also kind of drawing on there. Okay. So then these are the different kinds of angles you could draw in the unit circle. And notice how here's a negative angle. And again, this is like just imagine let's see if I could create a circle. Let's imagine this is on the unit circle. There we go. Cool. Let's just imagine that. These were the only like angle measure pictures I was able to find that kind of best describes it. But just see, we're just adding a circle there so you can envision that this is on a unit circle. And they should be all the same size. I just quickly made a circle. But so if I'm on the unit circle and I want to create a negative 60-degree angle, I just move I just move clockwise, and that's negative 60. If I want to create a positive angle like 135 degrees, you just move counterclockwise. What if I want to keep going around and around? You can do that, y'all. Do you know you could create angles that are larger than 360? You go around once, right? That's 360 degrees. You go around another additional, I don't know how much, and then you're at 570. You could keep going around and around on the unit circle and make larger and larger positive or negative angles, actually. So take a look at that. That's cool. And here's another example of a negative motion. So this was moving negative 270 degrees. So it kind of looks like a right angle right here. So why do we have to move backwards, or why sometimes do we have to have larger than 360 degrees? Well, the reasoning is right over here. So there's applications such as rotating wheels, where it's convenient to expand our definition of an angle. So measures can be any number of degrees, including positive and negative values, because we could kind of better apply it in the real world and create functions that represent repetitive motion. So that's why it could go more than just once around the unit circle. Let's see, does anyone have questions on this portion? Okay, I hope silence means we got this, not confusion. But hey, if you're confused, I am here for you, office hours, and or you could just ask, and I could stop the instruction and help us out. Okay, so then, um, mm, Now we're not going to do that. We're going to look at this together and do the checkout together. So ignore this 2-minute timer. I was actually going to have you all independently kind of explore this for 2 minutes, but due to time, let's look at it together. And then that's going to be our checkout. Okay, so what we're going to look at together is we're trying to ask ourselves this question. So, okay, cool. We talked about the unit circle. We talked about what radians are, but how does trigonometry, remember what trigonometry was? Remember those definitions? How does that show up on the unit circle? So I wanted y'all to kind of explore this using this tool, and we're going to add our thoughts on a Padlet. So let me explain this tool. This A right here is degrees. So if I want to go back to 0 degrees right here, I'm flat. I'm on the positive x-axis. And let's say I want to create the terminal side to be 1 degree. That's 1 degree. Let's say I want to do 30 degrees. So see how the terminal side is moving up? And I am creating a 30-degree angle. Using that tool, a lot of you are mentioning that there's degrees, radians, and right triangles that are coming up. And to remind you, trigonometry is the study of triangles and how triangles show up like basically everywhere. And there's measurements of the angles, radians. There is all forms of triangles within the unit circle, I'm noticing. We have the degrees that are showing up. I like this one here. Look at this. I like it just because it's mentioning something about a hypotenuse. Like, let's see what this is Henry's answer. So trigonometry shows up in the unit circle with the longest side, the hypotenuse of the triangle being the radius of the circle. That's deep. So that's deep. That's interesting. That's actually getting even.
I didn't get it.
And then hi group, sorry to interrupt. Sorry y'all, we're having a good discussion. I did add a few more students into this group. So if y'all if y'all can add their name to the first page, and then I'll be actually working in with one group who can't screen share. So yeah, I'll leave y'all to
Wait.
Okay.
Real quick.
That's how you spell your name, right, Risha?
Yeah, sorry if you were typing. So I went ahead and just put the question in there. So Sam says the edge of the circle is round. So maybe if you use the circle to measure the waves, I like that. So it's kind of like you're using something on the circle as a measurement to perhaps measure the waves. So I like that. So it's kind of like a little wonder there with a connection. Let me go ahead and put that in for our, oops, I guess it won't let me actually copy and paste. So I'm gonna just write it. So the edge of the circle is round. So maybe if you use the circle to measure the waves, question mark. Anything else like Ruben or Gabriel, if anything is coming up for you, anything else that we can add to this, or do you feel like we're set? So we have, oh man, I didn't even anonymize the names. Let me do that now. There we go. So we have a unit circle models waves because the degree of the number that may cause the sound on the line. Okay, so they're making some connection with the degrees of the number and may cause the sound. Lines are going through both have fractions with pi. So they both notice that the pi's are coming up through both. So they're just in general making some light connections. So it's interesting to see what everyone else is thinking. Let's go ahead and move on to the next part. Okay, y'all, let's go ahead and investigate. And I linked up a tool for everyone. It says, using this tool, we're able to create a sine function. How can you your team describe what's happening now when you open up the tool? So let's first look at the tool. Let's see what this is. Okay, look at this, y'all. This is pretty cool. So this right here is angle. Right now it's at 0 degrees, but if I increase my angle, let's see what starts to happen. So what do you think is happening here? Take a look. See, a wave is forming. I'll try to move it like slowly so y'all can see what's happening. It's a nice little visual tool so you could see how a unit circle or any circle is kind of creating a wave there. So there's our wave, and we could keep going. So it keeps going around and around, and it continues to make this wave. So it stops kind of there. So let me just go ahead and go back so we can start to pay attention like on what we think is actually happening when it comes to the unit circle and wave. So it starts off at 0. And then as we increase the angle, the idea is there. Let's see. So it looks like the line grows as you go around the unit circle. So you could use the length of the outside of the circle to find the length of the wave. Okay, that is interesting. And then we have from Ruben, maybe each time the line goes around the circle, it creates a wave. Ooh, I like both of those things. I'm going to go ahead and put them both in here. So I'm going to try my best to, I can't copy and paste. Let me try it. Let me see. Oh, I can. Wow, I'm BSing here. So here we go. I can copy and paste. I guess I just was unsuccessful the other time. So there's both of your feedbacks. So yeah, I noticed that there is a connection too, Sam, as it goes around and around, that line just grows and keeps increasing, just like the degrees or whatever is increasing. And I like that each time it goes around the circle, it makes like one wave. I love that. Let's put that in. And we could see so far for those groups that were here already, what they had attained. So we have the higher number, the bigger the curve is what's another group noticed. The higher number, the more waves created. Oh, so I guess like the higher each time we ran around, something similar to what Ryu said, Ruben, the more waves we got. We also have another group that says when exploring the tool, one can see that when moving the bar from the left to the right, it creates a wave. Whoa, due to the triangle making some sort of degree. So that's interesting. So cool. Grace's group says that lines are going through both. Not sure about lines. I don't know if you mean like these lines, like the X and the Y axis. And then it says both have fractions with pi. So there's another group that is noticing that connection with the radian and this X axis where they both have pi. Henri's group says a unit circle model waves because of the degree number may cause the sound of the line. So they're thinking there's a connection between these degrees and sound. Lastly, the edge of the circle is round. So maybe if you use the circle to measure the wave, so kind of using the circle to measure something in the wave. I really like Vivian's contribution there. On part 3, y'all were asked to go ahead and investigate this amazing tool that kind of visually shows you how a unit circle actually is making waves. So it's pretty cool. But our goal, and basically the hard part, is how do we kind of elaborate what's actually happening here? Like what is being measured? That's why I really liked Vivian's contribution there. So what exactly are we measuring when it comes to a circle and the fact that we're making these waves? So that was juicy. And so you all can take a look at this, but the ones I wanted to definitely point out is Grace's comment where it said the higher the number, the bigger the curve. Let's go ahead and see if that's true again. So higher the number. So for example, the green circle, right? It's all the way up at the top of the circle, see? And it makes kind of like a maximum on the wave. Then it goes down, 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 and it gets kind of like negative. Goes back around, and then again it goes to a high point on the circle, and notice that it makes another maximum and down. So I agree with Grace's sorry, I was with the group. So I agree with Grace's contribution there, that the higher the number is kind of like the wave is at a high point. And let's see, another group mentioned something about triangles, using triangles to somehow create the waves. And this one, it says as you go around the circle, you can see the length outside of the circle, maybe find the wave. And I like this one down here. Maybe each time the line goes around the circle, it creates a wave. So each time it goes around once, you get one wave and you keep getting more. So let's go ahead and bring everyone back to our slides. So thank you so much, y'all, for working in your groups. And I saw so many exciting things, but we're gonna go ahead and transition. So we're gonna know the connection between waves and unit circles next week in our class. So just keep this investigation in mind, y'all. Essential question. How is the unit circle connected to functions with waves? Remember this? Y'all did some group stuff. We were asked this question and you all were trying to figure this out. And we had an amazing stuff. And I know I was with the group last week. So that was a review of what we did. I know, right? In the picture. So that's what we're jumping into today. We're going to finally know the answer, y'all. Is formed by imagining a point on the circumference of your circle, like on Desmos, and you trace the vertical height of that point over some input such as time. So try to read that again to yourselves. I just read it, but go ahead and reread it, right? There's a lot going on in this. There is mentioning of circumference. Let me underline that. And there's mentioning of something of a tracing the vertical height. What do they mean by vertical height? And it says you have some input such as time. So let's make sense of that. And I have a little visual for you to help us make sense of that. All right. So that is the answer, everyone. So first off, y'all were trying to like figure out how the circle makes waves. This is the answer, but let's figure out why this is the answer. Like how, like what is this saying? Okay, y'all, I have a scenario for you. Ferris wheels. I know, hopefully we've all been on a, well, not hopefully we all know of a Ferris wheel, not that we've all been on one. So let's say we have a Ferris wheel. And let's say that on this Ferris wheel, you enter in at the bottom. Now, I live in Hayward, y'all. And one thing I miss after COVID started was we would always get like every October and like every springtime, there would be a fair that would set up in Southland Mall in Hayward. And they would always have a Ferris wheel. And I love going on the Ferris wheel. But anyways, over at the Southland Mall, how you would board the Ferris wheel was actually right at the bottom. So you would board right at the bottom. You have to get in quickly. So let's imagine that it's that very same Ferris wheel where you get on at the bottom. So you board it on here. Okay. And over time, right, you know that as you get on the Ferris wheel, you're gonna start at a height of 0 and then you're gonna go up. You just go up, 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 and you're gonna keep going higher and higher, right? Now I'm just pushing my, there we go. There we go. So I boarded here, right? Our board's here. Over time, right, you're just going to go around and around on this Ferris wheel. Let's imagine that over time you end up here and you're the rider. What is the height when we're talking about traces the vertical height? Take a look right here. It's going to pop up. So right here, imagine that I'm trying to measure my distance from the ground, my distance as the rider to the ground. Like what is the distance? Take a look here. It's coming up. Height. When I measure my height over time on the Ferris wheel, I get a wave. So that's how we could put this into context. Now, I want to also point out something. So let's say I'm on the Ferris wheel and I go all the way to the very top. Let's say I'm all the way to the very top. This very top part means I'm at the highest point that I can possibly get on the Ferris wheel. That means I am at a maximum point when it comes to the wave. So take a look. I started at a height of, I guess let's say it's meters. I started at a height of 0 meters. I go up the Ferris wheel. I reach my maximum height. Then my height is going to decrease because I'm going back down to my original starting position. I'm going back down. So back down. Until finally, I'm back to where I boarded. I'm back to a height of 0 where I boarded. And it looks like on this particular Ferris wheel, it took 3 minutes for me to get on the ride, go around once, and come back into my initial starting position. It took 3 minutes. Take a look at how this wave correlates to the graph now. What we're doing is we're mapping my height over time, or we're calculating the distance of that point over time. Sometimes it's not height, sometimes it's something else that we're measuring, but according to this image right here, it's height. So that is the actual connection. And what I have for you is actually the tool. So let's say my explanation with my little drawings is not enough, right, to convince you. So I'm gonna go ahead and clear my screen and show you the tool. So let me escape. Sorry, y'all. And here's the tool. I'm going to also share with you the tool so you can explore this as well and check it out. Oh, sorry, Danny. I just saw your comment. I remember wanting to go to the fair at Southland, but my fam always went to shop, not for the fair, and then being dead. Yeah, yeah, as a kid, yeah. But then now, dude, as an adult, I go on the Ferris wheel. Making up for all those times I couldn't go because my parents just went shopping. So I'm with you. Okay, y'all. So take a look. When you open up this little thing I just shared with you, you have this cool Ferris wheel app, I guess you could call this. What I'm gonna do is I'm going to move this all the way to say 0 minutes. Oops. So initially you're not at a height of 0. I guess you're at a height of 1.5 meters. So I guess there is some. You probably have to stand on something to kind of get it on the ride itself. So that's okay. Oops. Now, below this, you have the graph. Notice that your input, your x-axis is in minutes and your height is in meters. So take a look. So as I move this dot, as the time goes on, your height increases. Oops, oh my gosh, I don't know how to do this slowly. And as I'm moving it, notice how your height over time is getting graphed down here. Let me try to zoom out to see if you could see this better. Yeah, it won't let me. But yeah, you all have the link, so take a look. So you go around once, almost once. I have to get myself to, can I type it? No. I want to get back to, there we go. So I'm back to my initial position. Notice how that is equivalent to one wave. So functions that model these kinds of wave-like behaviors that we just saw with the Ferris wheel, they're called sinusoidal functions. That's a weird word, right? And sinusoidal functions are either sine or cosine functions. Take a look at how they're graphed here. Cosine is basically like a sine graph, except it's kind of just shifted to the left a bit. Take a look, cosine's in blue, sine is in yellow. I also want you to notice that your input can be radians, or it could also be degrees, or it could be time, like it was when we're looking at the Ferris wheel, remember? So it could also be time. It could be whatever the input is. So sometimes your input could be how many degrees you went around the circle, how many radians you went around, or it could be time like the Ferris wheel. So that's the only difference. Again, sine and cosine, they're known as sinusoidal functions. These are the two kinds of waves you can play around with. Next, let's go on to slide number 9. Unit circle and periodic functions. So periodic must be a new word for y'all. So what are periodic functions? That's going to connect to our big ideas because periodic functions are functions that create a repetition of values at regular intervals. So that's the formal word. One period or a period is the length of one of those intervals. So what I have for you right here, 2 examples of what we call periodic functions because they repeat over time. Visually, it repeats like a wave or it repeats like this, where it kind of looks like ghost heads repeating over and over. Different kinds of periodic functions. And y'all saw some of these on that decimal activity as well. And then Danny put, so 2 points back and forth. So do you mean 2 points? I'm not exactly sure of the question, like 2 points back and forth. Not exactly sure, but I will right now on the next slide talk about how we, I believe, find period. Let me know if you want to rephrase your question, but. I appreciate the clarifying question. Oh. Okay. Don't worry. I'm going to continue to talk about it. If your question comes up again, try me again. It could be just me. I sometimes have difficulty interpreting questions. So y'all, what is a periodic functions have something called a period. That's why they're called periodic functions. They have things called a period. Now, what is this period that I'm talking about? A period is basically the length and time that it takes for a wave to repeat its cycle. That's what it is. So y'all remember the Ferris wheel? When I boarded the Ferris wheel and I went around once, that would be one period. So in the Ferris wheel example, it took me 3